Okay. So today we are discussing the week 11 content for the deep learning course, and what was covered is deconvolution and image segmentation. I think that is what was mostly covered. So let's look at the first question, and if you have any doubts regarding the course content and what we discussed previously, then just interrupt and ask, or you can type in the chat. Okay, 1 second. So yeah, let's discuss the first question. For the given image, for the below image, you wish to apply color based segmentation. How many different regions can you expect as output? So what will be the answer? So the image is quite blurry, but we can make out it is some sort of a garden kind of thing. There are different types of flowers and some grass is there. And you want to apply color based segmentation. That is, you want to segment out regions based on their color. So if you segment out the regions based on their color, how many different regions will you get? So you will get one region which is of red color, another region which is between that, which is of white color, and this region which is of green color, right? Green color. This region is white color. Okay, what did I do? This is not there. Huh? This is white color. This is red color. So we have three different regions. So if you are using segmentation neural network architecture, convolution based, you want to identify, segment out the regions based on the color, then you will get three regions with distinct colors. So the answer to this is 3. Okay, that is the basic definition of segmentation. Okay, any doubts in this part? Okay, then I'll go to the next question. So this question says, consider the input image to a segmentation task. So this is the input image. Output of the below three outputs from the network. Out of the below three outputs from the network, which one is or are a possible segmented image? So there is this input image where there are three people standing on a beach. In the first image, the three people have been segmented out and there is a bounding box on each of the individual. The second image, we have the sky, the sea, the beach, and the people segmented separately. And a third image, each of the individuals have been separately and been given separate colors. So each is in some form of segmentation, right? So each one are possible segmented images. So we can say all three images. So what is the difference between the first and the second? In the first image, each of the individual humans have been given different colors, while in the second image, all humans are given the same color. Okay. And the first, the beach and the sea, those are not identified. While in the third, those are also identified along with each of the individuals separately. So when you are not uh, sort of segmenting each of the individuals separately, then you call it semantic segmentation. But if you are segmenting each of them separately, then you call it instance segmentation. Okay, I'm still connected, right? One second. So is there any doubt in this question? Okay. So I was using my phone for looking at the chat, but my phone got disconnected from the meeting. Anyway, let's go to the next question. So which of the following is true for semantic segmentation? Semantic segmentation meaning you only, like, you will give all humans the same color. You won't give different humans different colors or different labels. So semantic segmentation can be considered as pixel-wise classification problem. So each pixel you are classifying into one of the different categories. Like you have an image, and each pixel will you will classify into one of the categories. Like in the previous example, it could be a human or sea or sand or sky. There are four categories. That is when you're doing semantic segmentation. The B question is it has an application in autonomous driving, industrial inspection, medical image processing, etc. So yeah, when you are driving, when you are creating autonomous driving sort of software, Then whatever image you get from your camera or the video that you get from your camera, in each frame you want to segment out which part is the road, which part are the vehicles, which part are humans, which part are the street sign, the navigation symbols. So those you want to segment out, and then separately you want to identify what they mean so that you can navigate properly. In industrial inspection also you can find similar applications. In medical image processing also, like if you have a CT scan, then you may want to identify which part is the kidney, which part is the liver. So both the statements are true. Okay, so both A and B are true. Any doubt in this? Okay. So in a semantic segmentation, an image of size 512 cross 512 is divided into non-overlapping patches of size 64 cross 64. How many patches will be there? So what they're saying is you have a 512 cross 512 image, and you did semantic segmentation. So that means each pixel you try to classify into some labels. Let's say you have n classes, 0, 1, 2 till n classes. Each pixel can belong to one of the n classes. So you tried to classify them, and what happened is the resultant image consisted of 64 plus 64 non-overlapping patches. That is, the image got divided into patches, each of 64 cross 64. So let's say this all got 0, 0, 0. This all got 1, 1, 1. Maybe this got the label 3, 3, 3. Like that. So how many such patches can be there? So that is easy, right? You can just do 5 and 2 divided by 64. How much is it? Mm, it'll be 8 times, right? So you will have 8 here, similarly 8 here. So there will be 8 into 8, that is 64. 64 patches. Yeah, answer is 64. So it is like, it's like very unlikely such cases can happen, but some cases it may happen. Let's say you have a satellite image of some area. Let's say it is a farmland, and you want to identify different farms. You have some satellite image, and it's a farmland, and you have some different farms of some dimension. It may not be exactly square, but your algorithm sort of identifies different farmlands. That is just one random example I just thought of. So it's not as uniform as everything is 64 plus 64. Here the dimensions may differ. And then figuring out how many patches are there, that can also become slightly difficult. Okay, I think this was a simple question. Just you had to know what semantic segmentation will do. It will divide the regions into different uh, groups. So this next question is asking, class activation maps are used for. Class activation map is what? Was it discussed in the class? Okay, what it means is, when you have a convolutional neural network of some architecture, let's say you have this, and it goes and becomes something, goes, then you have final classification layer and you get some output. So for a given class, whatever intermediate features that you got, which regions got activated, that is basically the class activation map. So in the FCN, you sort of used the intermediate feature maps that you got. Let's say there was an image of cat and dog, and you have to identify the cat. Then this region will get activated, and this is dog, this is cat. So this region will get activated in the final layers if you are doing cat classification. And you segment out this region to segment the cat. So what are you using the class activation map for? You are using it for the accurate delineation of object boundaries, pixel wise labeling for semantic segmentation, improving prediction accuracy for CNNs on a classification task, identifying the image regions where the CNN attends to for making predictions. So we are not using it for C, right? Because the classification is anyway done. And you are using it to identify the region where the CNN attends to for making the prediction. You can then use it for pixel wise labeling also, and to delineate the object boundary also, right? So these are in some way used for semantic segmentation. So is this part clear? So a trained model, when the model, after the model training is done, you will look at the class activation map to identify from which region the model used to make the classification task. Yeah, you have raised your hand. You have a doubt. You can unmute and ask. Okay. So the class activation map is once you have trained your model for some task, some classification task, then when you give the input of, let's say this is your input image, this is your model, this is your input image. It has this dog and cat. This is dog. So one image is having both the dog and cat, and your model classifies it as cat because there is a cat in it. So what you look at is when you pass the model through the layers, when you do max pooling and convolution and everything, you will get certain feature maps. So in the feature maps, only some regions will have high value, others will have zero value because of max pooling and everything. So that feature map that you get is the class activation map. In some methods, what they do is they compute the gradient with respect to the label of that particular layer, and that they call it the class activation map. Otherwise, you can just look at the output also, and then you can, that can also be referred as the class activation map. So in the class activation map, only if this region is activated, that means only that region is used for making the decision that there is a cat in the image. So you can identify the boundary of that region, and you can use it for, like in the FCN 32 and FCN 16 models, you were using those intermediate representation, you are upsampling the intermediate feature maps to do the segmentation task. So you can use it for pixel level labeling for segmentation, and via that you're identifying the regions where the CNN attends to for making the predictions. So this ABD are like the same task in written in different way. Yeah, thanks. Okay, let's go to the next question. If WCK denotes the weight of the neuron corresponding to the Cth class in the classification layer for the kth input feature channel Fk, then the class activation map MCXY and the pixel location XY for the Cth class can be computed as. So you have finally a classification layer, and before that you have some intermediate representation that you get. So there can be multiple channels in that. So one of that channel is your Fk, And what they are saying is, so there will be multiple classes. So this is,
Hey Pranav, something to say.
yeah, yeah.
Can you hear me? What I want to ask here is like this number of channels. How do you determine if image is grayscale image, then it will have only one channel, and if it's RGB image, then it will have three channels.
Yes, yes.
That is something I know.
So in the input, as you said, like there will be some model here. What I am showing is some intermediate result that you get in some layer.
Okay,
Okay. So in the input, as you said, if it is grayscale image, you will have one channel. If it is RGB, you will have three channel. Or if it is some other format, the respective number of channels will be there.
okay,
And in the intermediate layers, you can decide the number of channels based on how many convolutional kernels you are using.
okay,
So that is a hyperparameter that you have to figure out.
okay, okay,
So if you use uh, like uh, some edge number of channels in some, like say first layer, let's say the first layer you have used some edge channels, that means the from the image in that layer you are trying to capture h different types of like features using h different convolution kernels.
okay. So that depends on the size of the image also, right? How many convolution I will be using. The hyperparameter that you talked about.
So it will depend on sort of the complexity of your task.
Number of images or the size of images.
It's like how abstract of a concept that you're trying to get. Like if you're trying to get some, the examples that I'm giving, like cat and dog, then you may require a lot more number of kernels, like some 32 or something. That is the usual number that people use. That is like some in the intermediate layer, the kernels that usually form will capture only basic shapes like a straight line, this kind of edge, something like that. That is what the kernels will learn, or some curve or something like that. That is what each feature map will separately learn in the image. And in the next layer, it will try to combine to form some sort of shape, like these complex shapes it will learn. So how many
Hmm.
different types of shapes you want to learn, depending on that, uh, you try to figure out the kernel. So if it's a simple task, like you want to identify circle and square, only that much, then you may not require that many channels or that many kernels, or even that many layers you won't require. So those are basic shapes. Even in two layers, you can find it out. But for much complex
Okay.
objects like car and dog and things like that, you may require multiple layers, each with many kernels. Like it will depend on number, how many classes you have basically, because each class will require certain different kind of shapes to be figured out.
Okay. So this OpenCV also has this kernel concept, right?
Yeah.
In OpenCV, so I think it is inherited from there.
So there the kernels that are used is uh, like in image processing, the kernels that are used is those kernels were defined by certain people for doing certain operations.
What they want to extract out of the image. Based on that, they define the kernels.
Yes, yes.
Okay.
So those
But
kernels,
yeah. Hmm.
they have predefined, like these should be the values, these should be the weights in that kernels. But in this neural network deep learning architectures, those kernels are your parameters of your model, and they are learned via gradient descent.
Okay.
So that is the,
Actually, it tries to identify the function out of the entire training process, right?
yeah,
Yeah, automatically identifies the function which gives the correct output, right?
yes. So how that function is identified is basically by figuring out what these kernels are.
Okay.
Like that kernels are what you convolute on your input image, and that kernel will have some weights, w11, w12, like that, and you do gradient descent with respect to these w's
Okay.
to figure out what parameters you update, keep updating the parameters, and when it converges,
Mhm.
that is your final kernel that you form.
Okay. Based on the conversions, this weight parameters will be determined, right? Which
Yes, yes.
based on the okay, cost
Yeah.
cost value should be list, and based on that, this weights will be determined.
Yes,
But
yes.
in case of image preprocessing, those weights we know like what we want to extract. Based on that, we will pass some parameters. Right.
Sorry, I didn't get your last part.
I'm trying to compare this scenario with plain image preprocessing. There
Okay,
we
okay.
do not find any function. Functions are predefined there. Here
Yeah,
we
yeah.
try to formulate the function.
Yes, yes.
Right.
Yes.
But internally, what function is generated, we will never come to know that. Internally, it will form some function in input and output, but
Yeah.
we will not come to know like what function is formulated.
Yes, that is correct.
That is not there.
Yeah.
Okay.
That's why these models are often called black box models, because we don't know exactly how it figured out, what it figured out, what it has figured out.
Okay, but wherein if I compare this with transformer model, transfer I am quite new to transformer, but if I compare this with transformer, still I come to know like how model is predicting particular cat or dog.
Yeah, yeah. Some interpretation methods have been developed for transformers based on the attention values.
Okay, but those are still black box, or those are because this the CAM method that you talked about in earlier question,
Mm-hmm.
class activation map.
Mm-hmm.
So similar methods are applicable for attentions also, right? Which attentions are responsible for the outcome.
Yes, yes, yes.
So those are so transformer based model is also kind of a black box model, is it?
In some manner, like for instance specific, like for each image you are trying, or image or text you are trying to figure out, right? But as a
Yeah.
whole, you don't know what is that function. That is what I meant.
Okay. Okay. Got it. Thank you.
Okay. So yeah, coming back to this question, what we have is you fed your input image to this model, and before the classification layer, in the pre-final layer, you sort of get an intermediate, uh, let's say, input with some like capital K channels, let's say, and Fk is one of the channel input output. And so WCK is the weights which are connecting to the Cth class. Let's say this is the Cth class neuron. That means this neuron will output a 1 or very high value when the image contains the Cth class, and it will output a value close to 0 when the image does not contain the Cth class. So the weights coming from this neuron to the Fk channel, that is Wk. Wc, what is the notation? Wck. Okay, weights connecting Fk channel output to Cth neuron. And that is what is written. The corresponding Cth class neuron, this WCK denotes the weight of neuron corresponding to Cth class neuron in classification layer for kth input feature channel Fk. Then the class activation map MCXY at the pixel location X5 for Cth class can be computed as. So at any location xy you will have the corresponding, and this is somewhere here, there is something, and this is location x, location y, and this is the pixel, like that you will have in each channel, each of the k channels. So the class activation map is basically what is the input from that channel going to that class neuron from this channel. The input that is going from here to here will be, from this location xy, will be the weight of that connection, right? And the feature value from that connection, that is the fxy value. And this you will do for all of the channels. So you'll have summation k. This k may be from 1 to capital K, if you consider capital K channels. Okay. So this is which option? So here as the class activation map at xy location only. So that is this option, right? What is the value of activation map at the xy pixel? That is the output going from the xy pixel to the cth class neuron. That will be the weight times the value at that location for that channel, and that will be summed over all the channels. This is clear. So the option is A. So what this measures is how much activation is coming from that pixel location. So the regions which have high activation coming, like the regions from which there is high activation coming, that is the region where your cth class object is present, isn't it? Or the model is considering that it is there. That's how the model has learned. Okay. So any doubts in this part? Okay. So intersection over union, also called the Jacquard index, is commonly used to evaluate the performance of object detection and semantic segmentation tasks. If TP is equal to true positive, TN equal to true negative, FP false positive, and FN false negative at a pixel level, Then IOU is defined as 1 and it is bounded in the range of, okay, I think this was not taught in the class, the intersection over union, but this is useful, so I just discussed this. So uh, like whatever input image that you have, you give it to your semantic segmentation model, and the output that you get, again the image of the same size, you will have regions which are segmented out, right? So let's say you have only two classes, so you will have regions with like background regions which are 0, and your object region will have 1 1 1 1 1, and again 1 1 1 1 1. So to evaluate how good this segmentation is compared to some reference or ground truth segmentation that you have, so this was your ground truth, 1 1 1 1 0 0, everywhere is 0, this is 1. Okay, this is your ground truth, that means some human has labeled, and this is your model prediction. So to evaluate this, how much this matches with this, what you do is this intersection over union. So that means you see how many of these pixels are matching, that is the intersection. So how intersection will be what? Here also it is matching, here also it is matching. That means here also it is 1 and here also it is 1. So that means that is a true positive. And here also it is 1 and here also it is 1, the same pixel, that is a true positive. So the number of pixels where you have identified your object and it is matching in both the places, that is your true positive. So that is your intersection. And union is the total number of sort of pixels which are 1 in both the places. So if you take the union, that means when you're taking union of two sets, the common elements are not counted same twice, right? They are only counted once. So that means if you see there is this region which is present in this but it is absent in this, so you will count all the pixels here, and you may say there is some extra region here which is present here, so you will count all these pixels. There is a region here which is not here, so you will count all these pixels. There is a region here which is not here, so you will count all the pixels here, 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 here. That is the intersection or union of this region and this region is, the union region will be something like this, right? And here the union region will be something like this. So all the pixels here, so that will be your true positive, it is all that is matching, plus I think this region is false positive because it is positive here but here it is negative. So plus false positive, plus here it is missing but here it is there. That means this is a false negative. It should have been 1 but it got predicted as 0. So that is a false negative. I think all the regions got covered. True positive is the intersection part. False positive is which was incorrectly predicted as 1 by the model, but it should actually have been 0. False negative is all those pixels which the model predicted as negative, that is there are no, the object is not there, but here actually it is there, so it is a false negative. So which option is it? B and C, right? These B and D, these two options are matching, but all these values are positive because they are count of the number of pixels. So the value will be greater than 0, and only when there is no false positive and false negative, when fp equal to fn equal to 0, you will get true positive upon true positive, which is equal to 1. Otherwise the value will be less than 0. Whenever fp and fn are greater than 0, this value will be less than 0. And when there is no, when true positive is equal to 0, your intersection over union value is equal to 0. So the range is this. So the answer is this. So when people try to compare different models on some data, which one is better, then they use this intersection over union of the model predictions. So here the intersection is like which parts of the model prediction and ground truth which are predicted as containing the object are intersecting. The number of pixels is your true positive. Any doubts?
There is some metric called IOU, right? Intersection over unit and mean average precision, MAP also.
And this is the intersection over union.
Oh, sorry, yeah, union, not unit, yes. The MAP is also another unit which I heard, like which measures average precision across all the images, right?
Average
How,
precision.
how it is different, how that is different than this one, intersection or unit.
Average precision, I guess precision is true positive upon true positive plus false negative, right?
Precision, yeah, means how accurately model like predicts.
I think precision is
Means
true
out of total positives, how many are actually positives? Total positives,
oh,
uh,
total positive means true positive plus
false positive.
true,
Uh,
this, right?
how?
This is
This is
precision.
precision, and there is something called mean average precision. Is there any relationship in this IOU and this MAP?
So I think here this false negative is also considered.
Okay.
And otherwise,
That is just the precision for all the image in that set, right? All the images. This IO is only for single image, right?
yeah, yeah,
This is only for single image.
yes. So you are saying, so here also when you say for a single image for image segmentation task, you cannot really define this term. I mean, you can define it, but when you're counting true positives, you still have to do it in this manner only. Like pixel wise, you count the number of true positives.
Okay. So any segmentation model, it will compare that true pixel or the pixel which is falsely predicted. It will do it pixel wise, is it?
Yes, yes,
For each pixel.
yes.
Okay.
Because otherwise, well, let's say you have some model. Like you consider this case only, where your ground truth is like this and your model prediction is like this. Now, at an image level, you cannot really call this as like only some region is missing, so you can't really call it as uh, a misclassification, right? It is a good segmentation.
Okay.
So that's
But
why,
when this image will pass through segmentation model, sometimes it will not be the exact replica of the original image, right?
yeah,
There will be some changes in that image.
yes. So when you do the pixel wise sort of computation, you will get a bad score for this as well as this. Number of true positives may be less compared to the ground truth.
Okay. So is that actually comparing with the same pixel from input, or how will know that, like number of pixels will be less in the segmentation output, right? Usually number of pixels in the input image and number of pixels in the output image will be same, or
So they
it
will
will
be
be
same.
different.
Like in general cases, in general model, what you try to do is you have your input image and you do your convolution operations, and that will reduce the image size. And then you do deconvolution and upsampling, right? Deconvolution,
Okay.
unpooling, or
Hmm.
some sort of upsampling to bring it back to the original dimension.
Yeah, so during this process, it will deteriorate the image also, right?
Yeah, but now you don't care about the internal features of the object. You just want whether that pixel is which class.
Okay.
You don't want to reconstruct back the original image. You just want to get pixel wise label, whether it is class 1 or class 0.
Okay, okay. I can just take the difference of these two images and see like what changes are done. Maybe
Which two
if
images?
I want to check the similarity in these two images, what what is lost? In fact, that is not so important because I'm interested in the region segmentation, in segmentation problem. But what information was lost during this process?
Okay, you want to measure that.
Uh, yeah.
That you can.
Okay. Got it.
Okay. Okay, then I'll go to the next question. How we create the target for semantic segmentation. So, yeah, so you had like when you're training your model, you need your input X, which is your image, and the label Y. So in segmentation task, what this Y should be? Y should also be an image of the same size as X. But instead of the pixel values, each pixel in Y will contain which label it belongs to. So the regions which a background will have 0 label, the region which has something else will have 1, and if you have multiple classes, then some region which is something else will have 2. If there are, let's say, 3 classes: background, object 1 and object 2. So how do you uh, but for your model, what you do is you give your input image, you feed it to your model, you get your output, and you use this y. Let's say this is your model output y bar to compute some loss function with respect to this. So how do you construct this target such that you can compute a suitable loss function? So to do that, what you do is you one hot encode it. That means if you have three classes, then you, and let's say this was h cross w, then you can construct 3 cross h cross w matrix where uh, this is y, then should not write equal to, let me just put like some arrow or something. Okay, so uh, y0 x comma y. Okay, this value means, or maybe just let me write one. Okay, y1 x comma y, this will be 1 if xy pixel is in class 0, y2 x comma y is 1 if xy pixel is in class 1, and y3 x comma y is equal to 1 if that particular pixel is in class 3. Okay, so for each pixel you will have a vector of size 3. That is what basically we are saying, and in that vector only one value will be 1, others will be 0. The first value is 1 means it is class 0 background image. Second value is 1, then it is class 1 image, first object. If it is like this, then it is a third class object, second class object, then class 2. So this is your target sort of label. So at each pixel you are doing this 3 class classification. So that means there are 3 neurons corresponding to each of the pixel, and one of them will be one which one has the highest value. If you are using softmax, you can find which argument or which of these neurons is having highest value. So how do we create the target for semantic segmentation? By one hot encoding the class labels, essentially creating an output channel for each of the possible classes. So there are 3 channels for each of the classes. So that is the correct answer. By labeling pixel of each class with different color. So now what does color mean? That doesn't make much sense, right? In terms of computation, color is something that we visually experience. In terms of computation, what do you mean by color? So this option doesn't really make sense. By creating list of all possible classes with having the index of the pixel belonging to that particular class. So that means it is saying for class 1 I should create a list which has all the pixels x1, y1, x2, y2 till some xn, yn is the list of all pixels it belongs to class 1. So that is not very feasible, because then how do you compute the loss? Because in here we can simply use some cross entropy loss kind of function and compute the loss at each pixel. But here it's not very straightforward how you will use the loss function. Okay. So only A option is right, because that is exactly what just now I had explained. One hot encoding. This is one hot encoding. Only one value is 1, others are 0. That is one hot encoding. The class labels and creating an output channel for each of the possible classes. So this original H cross W image you have created into 3 channels, each for one class. Okay. Is it clear? Okay, if there is no doubt, we'll go to the next question. Okay, in this they are asking, consider a semantic segmentation task on the following image to identify the regions with cars in it. There is an image, it has some highway and there are a lot of cars. What is the minimum number of class labels required for classifying each pixel? So we just want to, it is a semantic segmentation. We just want to identify the regions where there are cars, but we don't want to differentiate one car from the other. So then we will just find out, okay, this is the region, there is car, all these pixels between this region, they are cars, right? So how many labels do you require? Yeah, option C, right? 2 pixels, 0 for background, 1 for car. Wherever each pixel which has a car, you will put the label 1. Each pixel where there is no car, you put the label 0. So that is by definition of semantic segmentation. Okay. Okay. So in this question they are asking, consider an instance of semantic consider an instance segmentation task on the following image to identify and count the number of dogs in it. Okay, we have an instance segmentation task. That means we have to segment out the object, and we have to separate each one object from the other if there are multiple objects. And here what we are supposed to identify are the dogs. So if I identify this pixel as dog, then if to which dog it belongs to, all these pixels belong to one dog, while this dog is different from that dog. Okay, so this was background is 0, here it is 1, then this will be 2 because it's a different dog. So if m is the minimum number of class labels required for classifying each pixel, then m is what? Is m equal to 2, the minimum number of labels required for? Because here we also want to identify and count the number of dogs in it. So can we do it with m equal to 2 with only two labels? If we had only two labels, then we can only identify the regions which has dog in it. So we can't really use 2 pixels, we need more than 2. We also need to differentiate one dog from the other. So the second option is m is less than 5. So that won't help us count the number of dogs in this image because there are more than 5 dogs which you can see. M is equal to 5. So with equal to 5 also we can't do because there are more than dogs. M is greater than 5. So if we use some value of m which is much greater than 5 and much greater than the number of dogs in it, then we will be able to count the number of dogs, right? So in the output layer you will require some, and if I would the target as 10 cross h cross w, then I will have each channel is corresponds to one class. So I'll have appropriate number of class labels to identify one dog from the other and count the total number of dogs. Okay, so the answer is D. Is this clear? Any doubts in this?
So dog with the same color, will it be treated as one class or different class? For example, if there are three black dogs are there, right? So
So ideally, if you want to count the number of dogs, then you will want each of them to have different labels, right?
yeah, for counting that is fine, but that classification here, it's kind of unsupervised classification that happens behind the scene, is it?
No, no, no. You'll train your model in a supervised manner. So when you're training, you will have some images for which you have the labels.
Okay. I have all the, I will have the masks and the image and then, okay.
So when you're training, you will have a corresponding target sort of image where you have the regions separated with 1 1 or 2 2 like that for each of the dog. Here is a complex example. No one will sit and do this, but
Okay.
in many of the medical sort of applications,
Hmm.
people hire people to sort of create these target labels.
Okay.
They look at CT scans and they sit and mark each. Like they have some special tools for it, softwares where they can automatically just circle a region and all pixels in that region will get one label.
Okay, got it.
Yeah. So
But
that
behind the scene, it will not do any kind of unsupervised learning here, right?
no no
Unsupervised learning with the label data itself. No, that's not possible. Yeah.
no. Actually, it is supervised. Like
This
wo-
is purely
the
supervised.
methods that we have discussed, they are all supervised only.
And then if I use this trained model on some other image which is outside of this data set, for example, if I have cat image and my data set has all dog image, so it will not segment it because it doesn't have any dog in it, right?
Yeah, probably.
Okay. So the model will learn only the edges. It will just learn like what is there in the boundaries or something like that, or it will learn what is the object inside the boundary also.
So usually in the popular models, how it works is like convolutional based models. When you have um, some sort of convolution operations will reduce the image size, and then you will deconvolve, upsample, and everything, and you will get your target uh, output prediction.
Okay.
So each pixel, like if you sort of calculate, it will have uh, each pixel will sort of have a receptive field. Okay, it gets input from only this much region for the prediction at this pixel.
Okay.
So that means to mark whether this pixel should be 0, 1, or 2, it will consider this region, and based on that it will sort of make the prediction or decision whether that particular pixel, and that this pixel may be corresponding to a middle region over here. So in a sense, to predict whether this pixel is 0, 1, or 2, it considers this much region, which is the receptive field of that particular pixel in this image in the output. And the receptive field will be decided based on how you have constructed the your model architecture, what filter sizes you are using, how many max pools you are using.
Receptive field means the size of the kernel, is it?
Not exactly the size of the kernel. So you have some image, and once you used a 3 cross 3 kernel to get some other image, that means this pixel has used this 3 cross 3 region. Okay, so if you have only one layer, then it is the size of the kernel, that is your receptive field. But in the next layer, this pixel would have used, again, if you are using a 3 cross 3 kernel, then it will use this 3 cross 3 region. Okay, this pixel has used this 3 cross 3 region, where this pixel has come from some other 3 cross 3 region. So overall, this pixel in the original input image has come from this region.
Okay. So receptive field basically depends on in what layer it the pooling or that convolution is happening, right?
What is the kernel size? What is the max pooling kernel size? All these things will determine, uh, with respect to the input image, what is the receptive field of the output.
Okay.
So these are good things to think about when you are designing your uh, architecture, or if you want to figure out why some prediction is going wrong or something like that, you can check if it has enough receptive field to make that decision.
So, for example, if I take only the false positive, okay, now model has predicted some images which was incorrectly predicted. So, is there any way to trace back through these kind of receptive fields, like to trace back like where model went wrong?
You're talking about an image segmentation task.
Yeah, for image segmentation tasks, some of the regions are incorrectly predicted.
Yeah,
Some
so
other class level.
yeah, that can happen. Like it depends also. Uh,
That CAM or something can we use here? Class activation mapping. You talked about that earlier.
So,
Maybe if I want to, and I took one sample
mhm.
of one image where it was incorrectly predicted, and I want to see because of certain reasons that is incorrectly predicted.
uh So that can happen. For example, let's say it was this pixel. Is it visible? This particular
Yeah.
pixel,
Mm-hmm.
and but my receptive field was only this much. Okay. Now based on the fur, if I'm only looking at the this much fur, I can't say which animal it is. I need
Mm-hmm.
at least its head also to be there, or its
Okay.
legs to be there along with in the receptive field to make that prediction whether that pixel is uh, belongs to a dog or not.
The size of receptive field will be smaller as it progress from initial layer to last layer, right?
No,
So
no.
initial,
Receptive field will become bigger, na? So, for example, this pixel receptive field was only this much, but in the next layer,
yeah, it will go on increasing. So the last layer will give the bigger picture, right? Last receptive field.
so in the last layer, the
That's
receptive field will be the maximum
okay.
with respect to the input image.
And the cam is something we can place only on the last layer where it is about to predict the output. But we can also put it in the other layers also, is it?
So, CAM is basically you look at what is the activation or what is the output of the intermediate feature map. Like
Okay.
after you have trained your model, you just look at that.
After I train it, I will, okay.
So you might be training it for some classification, like not really segmentation. You have trained some model for some classification task, image
Okay.
classification or something,
Mm-hmm.
and then you look at the class activation map to find out for that particular decision to make that it is a cat image, which region did it use, and then you use that feature map to then do your segmentation.
Okay. Yeah, but basically what I want to understand is like I can place that in single layer, is it? Like just like I can take out the last layer and I place the cam,
Hmm.
and then I understand because of these certain regions output was this. So
Yeah, yeah,
similarly, can I do it for all the layers?
yeah. You can do it, but in the intermediate, the initial layers, it may not give that much good uh, activation. It may be spread across
Okay,
the.
it will because it will just give the only the smaller region where the features are extracted.
Yes, yes,
The local features, maybe,
yes, yes.
not the global features.
Yeah.
Right? Okay.
Okay. So if there is no more doubt in this part, then I'll go to the next question. So there are two statements, and we have to say which is true and which is false. So the first statement is in a max unpooling layer, the features are placed at the position from where the max pulled feature were taken. So that means you had some intermediate image, you did max pulling, let's say it was this, and you did, let me add one more. Okay, so let's say you did max pulling here, you got some value, you did max pulling here, you got some value, you did max pulling here, you got some value, and max pulling here, you got another value. Now after some time, after some layers, you got some representations and you want to unpull. So where it will place these pixels here, each the new pixels that you got, it will be placed at the positions from which these values were taken. So let's say this was taken from here, and this was taken from here, and this will be placed again here in the unpooling. Similarly, if this was from here, and this will go here, this will go here, like that. So I placed at the position from where the max pooled features were taken. So that is correct, right? The max pooling, what it did from this 4 cross 4 region or 2 cross 2 region, it picked the pixel value which had a maximum value. So this had a maximum value, so it picked that pixel value. In here, this had a maximum value, so it picked that value. That is the max pool operation. And then you did some more layers. You got some representation, and when you want to unpool, you save these indices in another matrix. Where you will put 0 1 0 0 because you picked the pixel from this region. 0 1 0 0. Here also you put some. So you picked this pixel from here. This was the maximum value in this 4 cross 4 region. Similarly, you did something here. So now when you're unpooling it, it will fill all the regions, all the 4 cross 4 regions with that pixel value, like the way it is implemented. This value will be filled in all. Let's say this was 3 4 5 6. So 3 3 3 4 4 4 5 5 5 6 6 6, like that. You will multiply these two. When you multiply these two, automatically, like element wise multiply, not matrix multiplication, element wise if you multiply, automatically 3 will only be placed here. This will be 0 0 0. You get 4 0 0 5 0 0 0 0 6. Okay, that is the unpooling operation. So the first statement is true. In the second statement, they are asking, in a max unpooling layer, the features are placed at the left top corner. They are saying every time the feature is placed at the left top corner. That is not true, right? It is placed from where you took when you are doing max pooling. So statement 1 is true and statement 2 is false.
Just if I compare this with autoencoders, okay,
Hmm.
their representation learning is the key there.
Hmm.
What is the difference? Like this is how it works there also.
In autoencoder, usually do we don't really use unpooling, right? Max unpooling.
Okay. I'm talking about typical encoder decoder architecture. Uh, Autoencoder may be one example, but maybe we
Ah.
can't use unpooling. Yeah. So essence of the question is like how it is different from the representation learning.
So in representation learning, usually what you do is you have some input, you use some intermediate layers to reduce the feature dimension, and then again you try to reconstruct your input. So x dash, you want to minimize x minus x dash. This is what you want to minimize. So if you are using this kind of max pooling and unpooling for this task, then you can call it as a representation learning.
Okay, I mean it is similar. Only the thing is there will not be any output as such. Right? Here we have segmentation output.
Yeah.
But this is something the intermediate output.
Huh.
But they also call something as embeddings or something.
Yeah, so
That embeddings is something like the intermediate representation, is it?
yes, yes. So what you are basically saying is this original input, which was in some R H cross W space,
Okay.
you use some function to embed it to, if this is a d-dimensional representation, to embed it into some d-dimensional space. So from R H cross W space, you have embedded your image to some d-dimensional space.
Okay. Compress means it is reduced, right?
Yeah,
First it will be reduced and then it will be increased in the decoder.
yeah,
Okay. But basically this operation, whatever we are talking about, those operations will be same only, right?
yeah, yeah.
Okay.
So when you are if you're using an unpooling sort of layer, then you lose this intermediate sort of values. So if you want to reconstruct your same image, then like max pooling and max unpooling may not be really useful.
Okay. So what is the alternative then?
You may want to stick to like some deconvolution kind of thing, fully convolutional network in the input also, and deconvolution in the output. The decoder, the encoder also full convolution, and the decoder.
It
But
will the inverse operation of the convolution.
yeah, yeah,
But instead of max pooling, if we use that deconvolution, then
yeah. So in the max pooling, there are no parameters. In max pooling and max unpooling, there are no weights. So that's why
hmm.
people use it. And in segmentation or kind of task, it's okay to lose some information. You don't want all the like many of the features you don't really want.
Okay. Okay, so that is the deconvolution and max pooling kind of a difference.
Hmm.
Okay.
Okay.
But then we can use this thing also, no, for segmentation, encoder decoder.
Yeah, yeah, you can use.
But you are saying that this max pooling, whatever we do using this unit kind of architecture, which is better as compared to sorry, the encoder decoder architecture, is it?
So that is in a way that is also an encoder decoder architecture. Instead of fully connected networks, you are using convolution, max pooling, unpooling. So encoder decoder basically means you are encoding it to some low dimensional space and then decoding it back to a higher dimensional space. That is what is encoder decoder.
Okay.
But if you are using only convolution, then the number of parameters increase, so it can be difficult to train. While when you
Okay.
use max pooling, because in segmentation you can lose some information, it's okay to lose information, so you can use max pooling.
Got it. Got it.
So you want to make your model as small as possible so that it is easily deployable in
Okay.
low computing
But
power.
then I think we can remove decoder once encoder is trained.
Hmm.
We can remove. I read it somewhere, but not sure about that.
That will be if you only want to use this representation, like once you train your encoder decoder auto encoder model, and you just want to use this representation for some kind of classification task. That is, you are classifying your original image based on this representation.
Okay.
So you don't really need the decoder.
Okay. Got it. Thank you.
Uh, Okay, this is discussing UNet, SegNet, which is not really taught. Uh, so the question is, consider the UNet and SegNet architectures which have been modified to have same depth and number of convolutions in each layer, and there are some options which are regarding the GPU memory requirements. So we can discuss this question. I'll just get the UNet architecture. Okay, this is the UNet architecture. Oh, okay. Okay, this is unit, and the other was SegNet. Here. So what are these two models basically? You have your original 572 cross 572 image, and this blue arrow is convolution. So you're doing convolution, image size decreases a bit, then again you do convolutions, it's 3 cross 3 convolution, and the number of channels you are increasing. That is this many different kernels you are using in those particular convolution layers. Then this arrow is max pooling. So max pooling will reduce the feature dimension. Here it is reduced to half because it is 2 cross 2 max pool. And then again you are doing convolution, and you keep reducing till you get an intermediate 1024 dimension input. Now when you are in the decoder part, that is from here to here, here you are using an up convolution, and so that you can consider as same as your deconvolution. And there is this gray arrow which is copy and crop. That means here you had a 64 cross 64 plus 64 representation in this layer. So you had a 64 cross 64 representation in this layer, but here this gets increased to only 56 cross 56. So what you do is you crop a 56 cross 56 part and you add it to this. That means you consider it as extra channels. So here there were 512 channels, so when you upconvolved it, again you might have got only 512 channels, but because of this extra 512 channels from here which you got from cropping and copying, you get total 1024 channels. Okay.
There is difference in this up convolution and deconvolution, right? Up convolution will upsample.
Deconvolution also upsamples. It is same thing, I think.
Only it's a naming convention difference, is it?
Yeah, yeah. think it is the same. Okay, I might have to check whether it is the same. But I think for this question it is not relevant. But you can check what is up convolution in this paper also. Thinking it is the same.
Okay.
So yeah. So that is about this unit. This is the unit. What is asked in the question? There is unit and there is segnet. So you have your regular convolution, max pooling, convolution option, max pooling. The extra thing is this copy and crop. That is, you cropped some part of the image and you copied it to the channels in your decoder part. And finally, you do up convolution, regular convolution, up convolution, and you get your output segmentation map. And this in this segment, what is happening is you have your convolution pooling, and then in this upsampling, which is basically your max unpooling, you are not doing this copy crop, you are uh, using the pooling indices that you used for max pooling. That is what we are discussed in this one, right? You do max pool, and then when you unpool, you are using from which index it came. So the information that is going from here to here is the indices, while from here to here the information that is going is this cropped copy and cropped image from the encoder part. So the question is saying consider the unit segment architectures which have been modified. So you have modified these architectures to have the same depth and number of convolutions in each layer. Okay, you somehow modified such that the number of convolutions is same in these two, and the depth is also same. This is how many layers it is. Then in terms of the GPU memory requirements, unit will consume less memory due to skip connections between the corresponding encoder and decoder blocks. So whether having these skip connections will result in less memory requirement than the segment. So that is not correct, right? Because here you are doing this copy and crop of this pixel, so you have to store this intermediate, or to say image, for each of these layers. While when you are doing this unpooling, you only have to store those indices. Even if you are storing in those binary matrix is 0 1. So for storing 0 1 you only need 1 bit, but these images will be floating point, which will be some 8 or 16 bit. So this statement is basically incorrect, that unit will consume less memory. Because of the skip connections, unit will consume more memory. Both networks will occupy the same amount. It won't. Segnet will consume less memory as it stores only the indices instead of copying the floating point encoder features. So here that copy thing is happening. The encoder features are getting copied. So that's why Segnet will consume less memory. So this is the correct answer. While D is saying unit will consume less memory as it does not require to store max pooling indexes. So as we discussed right now, storing the max pooling indices is less memory intensive than storing the intermediate encoder cropped images. Okay. So there were these two architectures which we hadn't discussed in the class, but we don't really need to know that much detail as to what these are. These both are sort of architects popular for doing segmentation tasks, and they have this encoder decoder kind of architecture, and they have this. I think this unit in particular has this special sort of thing that they have done, which helped them to improve the model performance. Okay. So any doubts in this?
Now this is clear.
Okay. Okay. This question is again there are two statements. First statement is in context of triplet loss for face recognition. Hard negative example is whose embedding is or are far from the anchor and belongs to same person as the anchor. So in that face net architecture, you are using a triplet loss function to train your model. Okay, this face net architecture, which was discussed in the first lecture of this week, you are using a triplet loss where what that loss function was exactly. So for every face image in your dataset, let's say it is X anchor is here. You consider one positive image which is the same class as the anchor image, and one negative image which is an image of some other person. So XA and XP are face image of same person, and XN is of someone else, and the loss function is something like so what this basically saying is your face net, it gives some intermediate embedding for each face image. Compute the square distance between the anchor image and the positive image, that is the face images of the same two different face images of the same person. Compute the difference between the intermediate embedding. You get some value, say diff p minus, you compute the difference between the embedding for the anchor image and the negative image, which is the image of some other person which is not the anchor. It's a diff n plus alpha. So alpha is some value that you set, some 0.05 something that you have set. So you want diff p minus diff n that you want to minimize, or you want it to have alpha distance. That is what you're doing, right?
See, in this case, I have a very basic question. Okay.
Yeah.
So this we can simply do the similarity matching here, right? Why we are training the model here?
Similarity matching in the sense.
Means if I can take one face image and if I take another face image,
Mm-hmm.
I can do some OpenCV structured similarity or something like that, and I can see the difference. What is the difference in there?
Okay, then in that case, you may like all the faces should be in the same orientation.
Okay.
And but
So here also, if I take one image of, from different orientation, then
so here the model will somehow learn the features which is representative of that person, irrespective of the orientation. That is what you'll expect,
okay.
irrespective of the orientation or lighting or like some glasses or something are there or not. You want your because this what to say, the deep learning model is not really doing pixel wise, right? It is learning some non-linear function to embed
Okay.
the image into some embedding.
So I can have one image. I can have one folder of some input images, and I have some query. So I want to say that
Mm-hmm.
there are some query images,
Mm-hmm.
and there are images which are already trained, right?
Mm-hmm.
So okay, I can pass all the query images at one time, or I have to pass one at a time, like that.
When training, you're saying,
While I want to inference, once the model is trained,
ha. So you'll have some database of some person images,
yeah. Hmm.
and let's say this f embeds it to some rd space. So for each image in your database, for each person, you embed the image or whatever vector that you get. So let's say it was a two-dimensional thing, then your database images will be somewhere over here for one person. For another person it may be somewhere here. For another person it will be here. So when you have a new image, let's say it is here, then you will say it is, because it is closer to this, you can say it is the image face of this person. Or you can put some criteria like distance between the closest image embedding should be less than some theta.
Okay, okay. And
Then
this
that
visualization I can perform on the query images, is it? Like to miss
on this.
which what cluster it is close to understand that I can plot that embeddings, is it?
So usually these embeddings will be very big, so you can't really plot it on 2D. You might have to use some dimension reduction.
Okay.
But to figure out, you don't really need to plot it. You can just compute the distance between the two embeddings in the original 1000 dimensional space.
So I can really use this to find out if there are some images which are kind of outlier images, is it?
Yeah, yeah. If the distance is too big from all of the images, like you
Okay.
you know all these images are within some distance of each other, but
But the query images are away from all these clusters.
yeah, some
Then I
per
can simply say that those are all negative images,
yeah,
right?
yeah, some image came and it is somewhere here, then it may be of some other person. It is not in my database.
But typically, can we use this? This is kind of what kind of learning is unsupervised, right? This is
No, this is
unsupervised.
supervised because you have. We are saying now XA is anchor image, XP is the belongs to
Negative,
this person,
positive.
XN belongs to some other person. So you know which images belong to which person.
So when I train this model, I have one pair of the image, right? One positive image and one negative image.
Uh, so usually, what you can have a bunch of images per person, and for each person, like when you constructing your mini batches for training, then corresponding to each image on your mini batch, within the mini batch you can find which is the positive sort of sample with respect to this, which is far from this, and which is a negative sample from this, which is very close to this. So you may ideally want to minimize the loss for that particular triplet.
No, no. With the example of this cat dog, if I take that example,
Huh.
I want to detect a cat. That is my objective to detect a cat.
Huh.
So, what will be the structure of the data set? Like one cat image as a positive image, dog image as a negative image. Is that kind of a structure will be there? Or
No, 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 no. So
I'm not.
this one is not really two class kind of thing. This is what to say. You have bunch
If I
of.
don't have that object in my training set, right? So that's where if I don't have that particular object and my object is unknown, right? So at that time I can go for this kind of a modeling process, right?
Yeah, that can be done. People have tried that sort of thing. But
But what I want to understand here, what will be the structure of training set?
so in training, let's say you have a bunch of images of object 1, a bunch of images of object 2, a bunch of images of object 3, similarly, a bunch of images of object n. Okay, this is your training data. Now you construct a mini batch out of this for your training purpose. In the first iteration, you constructed a mini batch which has some images from each of this. Okay,
Okay,
so in that mini batch, now for each sample you need to construct a triplet. Okay,
okay,
so first image, let's say it is from object 2.
okay,
So if it is from object 2, then in the embeddings that you get from the model, you look at which another image from the object 2, which is in this batch, is furthest from object 2. That means ideally I want my all object 2 images embeddings to be close to each other, right? All object 2 embeddings should be close to
hmm.
each other. But if there is some object 2 embedding which is far away from each other, then if this is my anchor, I consider that far away object 2 image as my positive. And if there is all the other images which are not of object 2 are negative images, right? So the negative image which is closest to my anchor, so let's say there is some object 3 image which is very close to my anchor, I consider that as my negative image. So now I have a triplet for object 2. Similarly, I consider triplets for each of the image in my mini batch, and I compute the triplet loss for each of the triplet.
Okay. So sorry, your anchor image is what?
So each image in your mini batch you will consider it as an anchor image,
Okay,
and corresponding to each you will find a triplet. It is a positive and a negative.
okay.
The positive belongs to the same class as your anchor.
But that object will be compared against each of these object 1 to object n, is it? Like
Huh.
which one is the closest one?
Huh. In your you because comparing against all in your training data maybe will be very expensive, so you do that within your mini batch.
within main image. Okay. And if there is a query image which is not part of any of these object 1 to object n,
So once you have trained, only then you will consider such queries, right?
then okay. Then it what will be the output like if that object doesn't belong to any of this? If
Hmm.
the embedding distance is very far from whatever we have here.
Yeah, so that may be a good example where you want to consider that object is not belonging to my known classes. Ideally, that is what we want. Whether that will happen or not, that we can't say.
Okay. This FaceNet is a pre-trained model. If I want to build my own model,
Hmm.
so do you know any architecture like which just for segmentation? I know you need segments. So if I want
So there
to
is a
train,
very simple sort of implementation of this FaceNet called OpenFace.
but this is for face recognition, right?
Yeah, yeah.
No, I don't want any face to be detected. I want it for some custom data.
The same architecture you can sort of you can use their architecture, but you can retrain it. You can reinitialize the weights and retrain it for your object classification task.
Okay. Yeah, that will help me to understand whether this data is suitable or not actually. This is really good. This is really useful. If I know that this data is very very far from what I have some explanation there, right? Why there is some issue with that image. Whether it's means if it is detecting or if it is not segmenting properly, I will know like why it's happening like that.
Yeah. So these models that like most the models that are discussed in the lectures, they are I think before 2016 or 14 or at that time. This is I think 2014 15 prior to that.
Yeah, yeah, but at least I should know the basic behind that.
Yeah, yeah. So
Recent model, I don't know what is the basic behind that.
so the more recent models have sort of piggybacked on these things only.
On top of that, they will
Yeah.
just refer this in their papers and they will say that.
But their performance improvements may like current model performance will be much better than
It is
this.
better.
Yeah.
Yes. Okay. It's the last question. We have more questions.
Two more questions are there.
Okay, okay. No problem.
So in this, what was asked was hard negative example is an embedding which is far from the anchor and belongs to same person as the anchor. So negative example does not belong to the same person. So this is incorrect. And hard negative example is embedding which is near to anchor but belongs to different person than the anchor. So that is correct. That is what we try to find here. A negative example which is close to my anchor and it does not belong to that same class. Belongs to a different person. So one is false and two is true. Okay. Here the question is which of the following operation does not reduce spatial dimension of features. So max pulling it does, right? From your image, when you max pull from this region, it will only pick one pixel and that will come here. So it will reduce the dimension. Then you stride again. So this does reduce. Convolution with 3 cross 3 kernel, stride equal to 2, padding all sides equal to 1. That means you have some image. Let's consider some 3 cross 3 image itself. Okay, and I have padded one that is I have padded. And if I do a 3 cross 3 kernel with stride of 2, that means from this 3 cross 3 I get 1 pixel. Then when I do stride of 2 means next will be this, so I'll get 1 more pixel. So again I'll get only a 4 cross 4 image, so that has also reduced the dimension. If I had used stride of 1, then I would do this, I'll get 1 pixel. Then next one I'll be doing is this, I'll get 1 pixel. Then the next one I'll be doing is this, so I'll get 1 more pixel. Similarly here also I'll get. So my original image was 3 cross 3. I used padding of 1 and I did 3 cross 3 kernel with stride 1. Again I got a 3 cross 3 image. So this did not reduce the spatial dimension. Average pooling is similar to your max pooling, so that will also reduce the dimension.
Okay. So if I don't want to reduce the dimension, then I can go for this.
Yeah.
But what is the significance of this? Why I don't want to reduce that?
Uh, so when you are using this stride, what is happening is if I am using stride equal to 2, after this convolution I am doing this convolution. So this region I considered and then this region I considered, but I did not look whether the kernel is finding something in this region. That is what stride equal to 2 does. And stride equal to 1 does in all the regions.
Okay.
But stride equal to 2 will be faster to compute. Stride equal to 1 will be slower.
Okay, okay. So just to save the memory, we can go for it, right?
Yeah, higher stride.
Okay.
Last question is which of the following operation does not increase? Okay, this is asking which does not increase. So max unpooling, it increases, that we had seen in the previous example. Average pooling does not increase, it decreases. So I should say average pooling decreases. Deconvolution also increases. This pixel shuffle is not discussed in class, but it also is a simple idea. Pixel shuffle. Yeah, so what it does is when you have this k channel, like 4 channels, it will sort of arrange them in this pixelated manner. So this is increasing in a increased spatial resolution. So people use this for improving the quality of bad quality images, which is also called super resolution. So what I am saying is I can just copy this image. This is pixel shuffle. So pixel shuffle also increases resolution, deconvolution also increases resolution, and pooling also increases resolution. Only average pooling decreases the resolution. Okay. Yeah, that was what was this? You have any doubt?
Now I'm clear.
Okay.
Yeah. Thank you, Pranav.